for the kind introduction. We will talk about thermoplastic forming of ceramic nanocomposites and also of microcomposites, and I will show some examples where is the problem. So the contents of my talk are, I will introduce the basics of thermoplastic forming, then give some remarks to nanocomposite related challenges. This will be repeated in the individual chapters, and then I will talk about rheology, debinding and sintering, indeed very interesting as Paul has mentioned this morning, and in the end give a summary and outlook. So the basics of thermoplastic forming, anybody knows how a injection molding machine works. You have the screw, plastification unit, here you have the mold, and in the first cycle we are just beginning to inject the polymer into the mold. Then here the mold is filled, the lock is on, and then here the mold begins to, the paste begins to cool down in the mold, and in the third cycle we are ejecting the samples, draw back the screw and begin to fill again. So what is thermoplastic forming? In this case, ceramic injection molding. This is molding of a plastified powder binder mixture by injection into a closed cavity of a defined size. So this definition gives a good introduction to the features of the process. You can see that the advantages are in a high turnover. We can produce a lot of samples in a quite short time with one shot ranging from 10 seconds to half a minute, let's say, depending on the complexity and the size of the part. We have a high reproducibility. We are injecting into a closed mold with a defined size and with a defined surface quality. And so we can achieve a high dimensional accuracy, and so this is a near net shape process. So the disadvantages, such a mold can easily cost between 10,000 and maybe 100,000 euros, depending on its complexity. And the whole process cycle is relatively complex. And the typical products produced by injection molding are mass production parts. For example, these parts from spice mills, precision parts, and something we have been working on in the last 5 years outside of IPN is orthodental brackets. So extrusion is a little bit different. The pastes may be quite similar. Extrusion is a forming of actually symmetric parts by pressing of a plastified powder binder mixture through a die. So what we can do is anything actually symmetric, tubes, profiles, bearings, filter elements, and things like that. The advantage is it's a highly productive process. So if you have to produce tubes of 2 or 3 meters length, this is the method to go. And the parts have a quite simple, actually symmetric geometry. And here you can see some machines. This is a piston extruder, and here this is a twin screw extruder. And on the other side you have this product spectrum which can be produced. So if you have a look at the flow chart of thermoplastic processing, it begins as always with ceramic powder, binder and additives. They are metered and mixed and kneaded, very homogeneously kneaded. Then we produce a granulate, and then we can start forming either injection molding or extrusion. Then in case of ceramic injection molding, we are separating the sprue and the runner, and then comes the debinding and the sintering. And all the stuff which is separated should be recyclable. And in the end, we have the sintering cycle and the final quality control. So some nanocomposite related challenges. If you want to injection mold, for example, ceramic nanocomposites, you have to develop a feasible method to produce nanocomposites for biomedical, mechanical engineering or other applications by a near net shape process in reproducible quality at low cost. Professor Gardo this morning talked about the problem of machining of nanocomposites. These materials are ultra hard, ultra tough, so it's not a big pleasure to machine them, so it's better to produce them in net shape. The the materials, they have been become available nowadays. We have affordable, high-quality commercial ceramic powders available. The near net shape forming method should have a high productive capacity, reproducible process parameters. Quality is always an issue. High surface quality, we want to avoid any machining. And if possible, we want to sinter by conventional atmospheric or controlled atmosphere sintering. So nothing pressure resisted. Only if these don't work, we may post-tip the components, for example. The microstructural features should be a dense microstructure. We want to retain our initial micro-nano architecture, so we want to stay somewhere below 1 micron with the matrix, maybe even finer with the dispersed phase. We want to have homogeneous microstructures, and we want to avoid structural defects. In case of injection molding, I will show you later, the main defects are pores and flaws. So what we can do is choose ceramic injection molding and extrusion. And of course, we can expect some difficulties, as always, when we treat nano powders. We can expect that mixing of homogeneous compounds will be quite difficult. The rheology of these nanoparticular feedstocks will be quite particular. And we can expect a lower packing density in the green parts than in case of microcomposites. These microstructures may have a lower homogeneity due to the inhomogeneous feedstock. And what we can expect is a more complicated debinding process and maybe a poor densification behavior despite the high sintering activities of our powders. So we start with the feedstock. Paul has given an example this morning. What is the requirement to an injection molding feedstock? We should have the lowest possible flow stress by adjusted feedstock viscosity. We want to form green bodies with a high dimensional stability, so we want to avoid warping, for example, during ejection out of the mold. We want green bodies with high strength and edge strength so that we can either take them out with an automatic handling system or let them fall into a bin. We want appropriate demolding properties. This means stuff shouldn't stick to the mold. We want low friction to minimize the wear. And of course, we have to trigger the optimum molding parameters and use an optimized mold design. So you can see here that these requirements are partially contradictory. You cannot have high solids loading and low viscosity at the same time, so it's always a compromise between different issues. So let's talk about rheology. Rheology is essential for understanding such a injection molding process. So the basics, anybody knows that. You have two shear planes, you have your body in between, and you move one plane in one direction with a certain speed. And then from this, you can determine here the shear stress and the deformation, and then define the viscosity, the dynamic viscosity, as a ratio of the shear stress through D, which is deformation, and here we have the kinematic viscosity. So we can define different kinds of rheological behaviors. The ideal one is the Newtonian one, which is number 1 here. Here you have a linear behavior. The shear stress rises linearly with the shear rate. When you have a shear thinning behavior, then you have a curve like this. So with high shear rate, the shear stress does not rise in the same ratio. If you have shear thickening, you have the opposite behavior. The viscosity rises strongly with high shear stress, and then shear thinning is something similar than shear thinning with flow limit. And we also have other properties which are interesting. Imagine a injecting such a viscous liquid into a capillary, and then you can see the evolving of such a flow profile. And this flow profile could either be a plug flow or a Newtonian, then it's parabolic, but in reality it's something in between. So in fluids with high solid loading, you have a transition from the Newtonian to a plug flow behavior, and you have all the stages in between. So you have all the opportunities between these two extreme cases, and so you need to make a correction for the non-ideality of the flowing behavior. And this is here an evidence given by polarized light texture analysis. You can see that there is a different grain orientation in the bulk and in the border of a molded alumina part. Another correction which has to be done is this Weissenberg-Rabinowitz correction for non-Newtonian behavior. We are plotting the shear rate against the shear stress, and this is a correction for this non-ideality. So in fact, for all real systems, this factor S is bigger than 1. You can see here, here's a 4, here's a 3. If S is bigger than 1, then the true shear rate is higher than the apparent shear rate. So the true viscosities are always lower than the apparent viscosities measured. Fortunately, in most of the sophisticated rheometers, this process is done by the software. So what is the correct method to measure the rheology of such a highly loaded feedstock? This is a plot taken from the book from Schramm, which is not publicly available. You can see that here at low shear rates you may be able to measure the rheology with cone plate rheometers, but at high viscosities, as they are in extrusion and injection molding feedstocks, you have to use capillary rheology. So how does this setup for capillary rheometry look like? So we have two possible setups. The one is a rectangular slot nozzle. In that case, you have two measuring devices for the pressure in a certain distance, delta L. You have the flow rate of the feedstock through the capillary, which is Q, which is something you measure as a mass per time. And on the right side, you can also do this with a round capillary nozzle. In that case, you have a pressure measurement at the beginning, and at the outlet, you have the atmospheric pressure, so your P2 is defined, and then we can use these two alternative methods to make a measurement of your rheological parameter. In case of capillaries, we have these equations. This is not so important at the moment, but it's quite straightforward from the theory and of the geometry of these nozzles, and this is how such a capillary measuring unit looks like. Here we have a heated compartment. The feedstock comes out of the extruder right here. Anything is heated at a certain temperature. Here we have a pressure sensor, and here we have a pressure sensor at the inlet. What we need is this one. This is just an additional one. And here comes the extruded feedstock, and this is this mass of the feedstock is determined every 10 seconds by just putting it on a weighing device. So the second correction we have to make is if we take such capillaries and just measure with one capillary length, then we have a problem with the fluid dynamics at the entry and at the outlet of the capillary. So we make a correction to extrapolate to a capillary length of 0, and this is the Bagley-correction, also done by the software. So I just give you some examples about microcomposite feedstocks and submicron composite feedstocks, and also submicron nanocomposite feedstocks. The powders we used were a 1.4 micron standard alumina or broken alumina, not a very pleasant material, but a very cheap material. Then a high-end submicron powder with 400 nanometers, and the two state-of-the-art submicron powders produced by Tozo with secondary particle size of 350 nanometers. And we also took two nanometric zirconia qualities. And what we produced was always a feedstock with 90 volume% of alumina and 10 volume% of zirconia with 1.5% yttria. So it's always a mixture of 50-50 of the zirconia, and the rest is alumina. So if we look at the microcomposite recipe, this is the coarse-grained alumina and the two Tozo powders, then we can see that we can make a feedstock of quite high solid content, almost 87%. And if we have a look at the shear stress against the shear rate, then we can see that the viscosity curve is more or less divided in three parts. We have an initial state with a constant shear stress over the shear rate. This means the stuff is shear thinning. Then we have either a Newtonian plateau, depending on the slope, or a slight shear thickening. And in the end, we have shear thinning behavior again. If we make a double logarithmic plot, it looks like this. And what we can say is that this region 1 is dominated by binder-particle interaction. The second one is binder-dominated. And in the third one, we can predict that this is determined by wall sliding. If we go to the submicron composite, then we can only observe two regions, because the third region is out of the range of measuring with this setup. And we can see here shear thinning behavior at the beginning, up to a shear rate of about 90 1 per second. And then we have either a low slope at low temperatures or a higher slope. This means in that case we have either Newtonian or shear thickening behavior. And the third part of the curve is something we couldn't measure. And in that case, we could still retain a quite high solid content of 85 mass percent, slightly less than with the microcomposite. And in the third example, if we look at this one, this is the same alumina as before, but we have here 10 volume% referring to the solid of nanometric zirconia, and the total mass percentage of solids was 82%. In that case, the microcomposite we had 87, with the submicron we had 85, and here we have to go to 82. So what we can see here is three regions again. The scale is a little bit different, and we had a shear thinning behavior at the beginning. In that case, binder-particle interaction. In the second region, Newtonian plateau or slight shear thickening, and then a shear thinning region 3, which ranges to a very high shear rate. So what is even more important is having a look at the machine while you make the experiment. When we compounded the paste, we had the impression this paste is too dry. We have to add more binder, but we shouldn't do that. And I tell you why. At low shear rates, this stuff is very brittle. It doesn't come out as a strand from the nozzle, but it just crumbles off. Then we have a stable region. This is the region 2, where we have normal extrusion behavior. And then we have extensive wall sliding and segregation. So at high shear rates, we have not extrusion of a strand, but it's splashing out of the nozzle. So what we could say is that controlling of the rheology of such a paste is extremely difficult. So how does this affect the microstructures? We can see here the microcomposite, quite nice, not too many defects, not too many pores. This is the submicron composite, still okay. But here I have a look at this nanocomposite, the submicron alumina with the nanozirconia. We have a lot of defects, and if we have a look at the SEM picture, we can see large holes, and these large holes do originate from separation of binder, from binder segregation. So these two are almost defect-free. They are okay for an injection molded or extruded component, but this ZTA3, this nanocomposite, contains a lot of micro and macroscopic defects. And we can trace this also to the mechanical properties. The number one, of course, very coarse-grained alumina. You couldn't expect a miracle here. It's just 300 megapascal. It was quite dense. K1C 4.2, it's okay. The second one, the submicron composite, slightly higher strength. Density was okay. K1C of 5. And the third one, in order to get at least these 320 megapascals, we had to do a lot of optimization work and the sintering. But of course, you have seen the microstructure, you cannot eliminate all these flaws. So the strength is very moderate. And due to the holes, we could not determine fracture toughness by indentation. So let's talk about mold filling and textures. This is the next step after you have determined the rheology behavior. When you're injecting into a closed cavity, and the cavity walls are cold, so you have to fulfill all these conservation equations, and you're injecting your paste into the mold. Here you have the freezing at the wall, and you have the no-slip condition. This means the velocity of the freezing material at the wall is 0. And here you have the profile. This is something derived from someone who was doing research on thermoplastic materials, not on ceramic injection molding. And this flow behavior is called the fountain flow. So the material in the middle stays on track, but the other material is traced to the outside. I will show this in the next slide. When we are filling such a plate by injection molding, we can see here the flow front, which runs through the mold while the mold is filled. And you can see here that the material, the flow lines, are drawn to the outside. And this is a more extreme sample. We have here a volume element, two planes, and during the mold filling, something very interesting happens. The material which is below this volume element, it surpasses the volume element if it's in the middle, and this fraction of the material here, this is the content of this flow element. The same happens if you're injecting a round particle of maybe a different color of a thermoplast by thermoplastic injection molding. You can see that this particle with proceeding form filling is deformed, and that it finally will be located in two pieces on the mold wall. So what does this mean? This fountain flow results in a flow profile with a flow direction parallel to the injection axis in the middle and perpendicular to the direction of the injection at the mold wall. So this was thermoplastic injection molding just with the polymer. What happens when we add a powder? The ceramic powders, we can assume, have either by their genesis, by either breaking of larger particles by breaking and milling, they have a preferential axis how they can be split, or a cleavage axis. So in case of broken powders, we can say that, of course, these powders will have a preferred crystallographic orientation depending on their shape. In case of precipitated powders, we have a preferred growth along crystallographic axis. So this is not true for cubic, of course. There you have isotropy always. And these anisotropic grains will take a position of minimized resistance to flow if you feed them into a flowing polymer. So there is a preferred flow orientation in the volume increment of our SIM component, and the grains will be oriented, resulting in a certain texture. These textures will be amplified during the sintering process. So you don't necessarily have to have a large texture in your green body. But if you have, let's say, 1% deviation from the average, during the sintering, you will have a strong orientation of your grains in the component. So ceramic injection molding components will have locally anisotropic properties. So these anisotropic properties, something we call textures, and how to visualize these textures. For example, in case of alumina, we can produce thin sections of such a sample, and this thin section can be studied under polarized light. You have to apply a filter, and then you see a color distribution, and this color distribution coincides with the orientation of the grains in respect to the polarization direction. So what we find out is an inclination angle of individual grains with respect to the injection direction in different regions of the sample. In that case, this is a part of an injection molded dog bone. You can see here a large flow texture with a different orientation than the bulk of the rest. So let's go back to the component. This is a very simple component. This is just an injection molded ring. And if you have a look at the complete part with the sprue and the runners, you can see that it's injection molded at 2 points located in 180-degree angle with respect to each other. So we have a pinpoint gate here, we have a pinpoint gate there, and of course we are injecting from both sides. Somewhere these two flow fronts will collide, and in that case we are producing a stagnating weld line in 90 degrees position to the gate. So what happens to the texture? In such a flow front, you can see that the particles are at the flow front, oriented in a 90-degree turn position to the bulk. And this is also true for all the outside of the component. So on the outside of such an injection molded component, all the grains are standing with the Z-axis upright to the mold wall after sintering. So this is obvious that this will lead to different properties of such a material if you compare it to an isotropic sample. So let's have a look at some special places here in this component. You can see here the gate. This is this region, and you can see the material is injected here, flows in both directions. You can see here that there is a dead zone and that the material flows away in both directions. And what happens in the region in between, where the flow is almost undisturbed? And here you can see this typical fountain flow behavior. In the middle, the orientation is in this direction, and the closer you come to the wall, the more inclinated the particles are to the outside. And on the outside of the mold, it's standing in 90-degree position upright to the wall of the mold. Something very interesting, which we just begun to consider, was the evolution of residual stresses during the mold filling. This is something which is known for years in case of thermoplastic injection molding. And if you look at such a process, this is the beginning at 0.7 seconds. This is a component, just a plate. Here is the midplane, and we start filling from here to there. And you can see here the evolution of residual stresses during this mold filling process. And in the end, you have a very strange behavior. You have a compressive stress at the outside, then you have a region of tensile stress and have a compressive stress in the inside. And if you go from here to there, the stresses are very high. They are about 15 megapascal, which is a lot for a green component. So Paul mentioned this morning, there are often people coming and say they have debinding problems. This is one of the debinding problems, because if you debind such a component, it becomes very unstable. And if you have these high stresses, then you will produce cracks below the surface, and you have cracking of components. And this evolution of stresses is even worse during the packing phase. This is the holding time when you have filled the mold. So some critical design features in ceramic injection molded components. You can see here different kinds of weld lines. We're injecting here, injecting there. It's the same case as with the ring. And then we have a stagnating flow front here in the middle. Another case is if we inject around an insert. And then behind the insert, there will be a flow front evolving. Also a stagnating weld line. And if you are injecting through two gates, then you will produce a weld line right in between. Something which has to be avoided in any case is free jet injection. If you have a very small gate and low viscosity and you have a big mold, so you're filling with a high pressure to get it filled, what will happen is that you don't have a flow front in the classical way, but that it's just spraying inside, and then you have this feedstock sausage rolled around in the cavity, and between these individual tubes, you always have flow fronts. So your component is a single flow front. So in such a case, the mechanical strength is very lousy. And a little more exotic case is if we have different wall thickness, you may have a weld line also, because the material flows quicker in the thick channel than in the thin cavity. And what's also a problem is abruptly changing cross sections. Then you very often have some cracks here in this region. So let's talk about debinding and sintering. So the critical issues, you have seen it in the talk of Paul. The binder we use should not stay in the component. It has to be removed. So it's a temporary binder, and we have to remove this binder without damaging the component. So, and to achieve this, we can use different kinds of methods. The classical method is the thermal debinding. You just put your part into the furnace and slowly heat up and hope that it doesn't crack. So then you have a very slow propagation of the oxidation front into the part. And it's obvious that the temperature control of such a process, especially if it's a part with a high wall thickness, is quite difficult to avoid any pressure buildup in the inside and a bloating of the part of the component. What was invented some years ago by BASF was a special binder system based on polyoxymethylene. This is polymeric formaldehyde. And this polyoxymethylene is then decomposed by some acids which are added in the vapor. So then you just monomerize the polyoxymethylene, and in that case, it's from the debinding standpoint, it's a very elegant process. You can produce very thick walled materials because the debinding fronts, they just run from the outside to the inside, and it's quite easy to debind thick wall parts. The problem is these acids. If it's formic acid, it's okay. In some cases, it's nitric acid in some of these binder systems, which have to be combusted afterwards, so you have to have some special furnaces. The system we prefer is a combined system. This is a combined system of solvent debinding and thermal debinding. So in the first step, you do a solvent debinding, in most cases with water. And by solvent debinding, you are dissolution or extracting a part of your binder from your part, and you're creating an open network of porosity. And this open network of porosity allows for a safe thermal debinding. So we have a quite easy and safe post-treatment. So what's so special about nano in debinding? We made an interesting experiment. You may remember some of these compositions. We took the pure submicron alumina, added 5% and 10% of nanozirconia, and made a thermogravimetry and DTA measurement. And you can see here in the thermogravimetry, the differences are not so big, but here, if you look at the heat flow, you can see that there are big differences between these three types of feedstocks. You can see here the blue one with the highest content of nanozirconia. This first peak appearing at low temperatures, just 220 degrees, is much, much higher than in case of the pure alumina or the alumina with a little amount of zirconia. So you can expect that the binder burnout starts at a lower temperature and runs with a higher velocity. This is also something obvious. All these oxides, they have a kind of catalytic behavior, and if we add a lot of zirconia with a very small grain size, then the surface area introduced by the few percents of zirconia will be even higher than the surface area of our matrix material of the alumina. And all these active surfaces will contribute to acceleration of the binder burnout. So you have to be a little bit more careful if you use some feedstocks with nanometric components. Concerning sintering, in sintering, these lower grain sizes of our nanocomposite materials should be used to achieve an improved sinterability. So, but we have a big problem, and this is rheology, as we have seen. So by introduction of high surface area powders, we need more binder. And if we add more binder, then the solid content of our paste will be lower and the green density will be lower. So in extreme cases here, the benefit of nanopowders may be overcompensated by that. And pressureless sintering of nanocomposites with the very fine-grained additives may become very tricky, especially in such cases where other boundary conditions have to be fulfilled. For example, at ZTA, you should limit the sintering temperature to a certain limit to avoid the growth of the zirconia. So what we can do is apply some special sintering techniques, such as two-step sintering or two-stage sintering. Two-step sintering is holding quite a long time at a low temperature, let's say 800 degrees for 1 or 2 days, and then make a conventional sintering process. The other process proposed by Chen some years ago is especially for single-phase nanocrystalline ceramics. And here you going up very quickly to a high temperature, hold for a very short time, densify to about 75% of theoretical density, then lower the temperature, and then hold for, let's say, 12 hours or something to eliminate the rest of the porosity. And thereby you can achieve dense nanocomposites without final stage grain growth. So in such cases where this doesn't work, one may still use a sinter hipping process, so that you just sintering your injection molded components to such a state where you have no open porosity, and then make a subsequent hipping process, which is not too expensive. It's still more expensive than pressureless sintering alone. So what we have observed is that this two-step sintering leads to a complete densification of nanocomposite zirconia toughened alumina at lower temperatures. And the difference here between the nanometric addition and the submicron powder addition was quite significant. In case of these powders, we could see that there was an onset of about 50 Kelvin by employing nanocomposite powders, but these were not injection molded. No, they were injection molded, but the zirconia content was much lower than 10%. It was just 3 volume percent. Oops. I think some graphs are missing. They have got lost somewhere, but I will explain what you would have seen if you could see them. These were some dilatometry results, and you can see that with timicron DAR, it's alumina of 150 nanometer grain size. You have a sintering behavior which is absolutely conventional, and then if you add a small amount of nanozirconia, this came from Kolarobia, still you have the same behavior, and with 3% you have a very strange behavior. You have a crossover of different sintering lines. We have always tested with 2 Kelvin, 5 Kelvin, and 10 Kelvin, and then the sintering behavior becomes absolutely unpredictable. So with different sintering rates, these two constituents, they show a completely different behavior. So to give you 2 examples from in and outside IPN nanocare, on the left side you can see a sample of translucent alumina. We have developed this with a German company, and you can see here the part is extremely complex. In this case, where we have the clip, you have just half a millimeter of ceramics in between from here to here, and it's quite nice when it's applied on the tooth. The part almost completely disappears. And something we made in nanocare was these injection molded carbon components for seals and bearing rings. This was done in cooperation with SGL Carbon. You can see here, maybe you have seen it in the film on Monday. This is the pilot plant compounding done at SGL. Here, injection molding at SGL with a automated molding machine, and this is here the green part, and this is the sintered component. And the interesting thing in these nanostructured carbon components is that you can produce such seals in a very high quality. The bending strength of such a material is in the range of the best fine-grained graphite you can buy at the market, and it has a near net shape processing capability, but we think that there is still some room to improve this. So just let me give a summary and outlook. Ceramic injection molding and extrusion are highly efficient manufacturing technologies for ceramic components. Small components of narrow dimensional tolerances and high geometric complexity can be produced by ceramic injection molding with a high productivity and reproducibility. The form filling and the component cooling in ceramic injection molding are transient processes with rheological behavior depending on time, position, and temperature field in the mold. The fluid dynamic and the thermorheological boundary conditions lead to a structural inhomogeneities, such as textures and residual stresses, which you cannot avoid. So compared to, for example, cold isostatic pressing or gel cast parts, in ceramic injection molding produced components, you have to suffer a certain trade-off in strength, which has to be accepted. This is the price you pay for the mass production capability. Thermoplastic extrusion is an attractive method to produce actually symmetric components such as tubes, profiles, or blanks for subsequent machining in a very economical and efficient way. And components produced by thermoplastic extrusion show a similar level of strength and reliability as ceramic injection molding components. We were quite surprised about that, and are by far superior to cold extruded components produced with cellulose water-based binder systems. So the outlook. Ceramic injection molding has become a well-established process in the ceramic industries. However, the theoretical understanding of the process is way behind the research carried out in polymer science. So, for the future, modeling and simulation of form-filling behavior is essential to design molds and molding processes economically. So, if one mold costs you 50,000 euros, you cannot make too many faults unless you are losing your economic basis. So these simulations will help to come to a proper mold design and also to find initial conditions for the molding behavior for the machine parameters, for example, which make it much easier to implement such process into industry. So the future will require the development of suitable rheological models, the implementation of these models into mold filling simulations, and also, if we want to use nanoparticles, at least to a certain extent, we have to adapt the commercial binder systems and develop new binder systems, and to develop suitable recipes for nanocomposite materials. You have seen it's not so easy. You cannot just say, okay, if the surface area rises, then just add 1 or 2% more of binder. Because you have to consider the whole range of shear stresses, and it may be working in a certain range, but it won't work in the whole range. So adjusting the recipes will be mandatory. So something to be considered by the powder producers. What we do not need is finer and finer and finer nanopowders. I don't need any stuff of about 10 nanometers for injection molding. What we need is something closer to the border of the submicron range. So what we need is something between, let's say, 40 and 100 nanometers. If you put in, let's say, 10 or 20% of 100 nanometer or 80 nanometer powder into injection molding feedstock, your rheological behavior will not be killed. If you are introducing the same amount of a 10 nanometer powders, you can completely forget it. So these nanopowders have to be tailored with respect to the necessities of the molding process. So thank you for your attention.